Okay, so last time I was solving a problem. I made a mistake. I wrote a comment below the video, but I don't know, might you haven't seen that. Do you remember I was talking about intuitively you might be able to say that when the function is increasing and decreasing, you really don't need some time to use the derivative. I just gave you this function. Yeah, I was actually myself was confused probably a little bit. I asked you, is this function increasing or decreasing? Yes. So we thought that what is the meaning of increasing function? If I increase x, f also increases, then the function is increasing. And if I increase x, but the function decreases, the function is decreasing. Yes. But then I made a mistake. I said that, okay, when I increase x, what happens?
It's decreasing.
This seems that this is increasing when I increase x. And then the denominator goes up, and then 1 divided by that goes down, yes? That was the idea. But that is not totally correct. I was also confused. In Math 4, when I wanted to solve it using derivative, then I realized that something is going wrong. I did it, so this is very good, that it is very good to have something, a mathematical theorem in your hand. Okay, the reason, do you understand why now? Why this idea is not correct? When I increase x, there is no guarantee that this is going up. Because x squared is not that kind of function. If you increase it on the positive side, yes, it is going up. But if you increase it on the negative side, it goes down. Yes. If I ask you what is the graph of the function, so you see the graph of the function x squared is something like this. Yes. So it is clear that when I increase the value of x here on this part, x squared is increasing. So of course, then this is increasing. It means that 1 over this is decreasing. But when I am on the negative side and I start increasing the value of x, the value of x squared is going down. Is that understandable? So let me, if I want to give you another idea. So for example, let me calculate f of minus 1, f of 0, f of 1. Yes. So of course, minus 1 is smaller than 0 and smaller than 1. Yes. If the function is increasing, this means that f of minus 1 should be smaller than f of 0, should be smaller than f of 1. This is the meaning of increasing function, yes? I am increasing the value of x. I am expecting that the value of the function should also increases. But what is f of minus 1? It is 1 over 1 plus minus 1 to the power of 2, which is 1 over 2. What is f of 0? It is 1 over, so it is just 1 simply, yes? And if I put f of 1, the answer is again 1 over 2. So you see, from here to here, the function is going up, and then suddenly from here to here, the function is again going down. Yes, you see, minus 1 is smaller than 0. 1 over 2 is smaller than 1, that's okay. So, but then from 0 to 1, the function, the value is increasing, but the function is going down. So that is actually when I wanted to solve the same problem in Math 4, because they know how to take the derivative of this function, I realized that I made a mistake. And of course, that is clear now, yes? But what we can say that if x is positive, then this function is decreasing. If x is negative, this function is decreasing. It's a very good exercise. Draw this by GeoGebra and investigate that is correct. So you need to be very careful, but that idea is still standing, okay? So that is what I wanted to correct from the previous lecture. Okay, now let's continue our lesson again. So today we want again to talk about local extreme and terrace points in a systematic way, okay? So do you remember what was a local extreme point? Local extreme points are two types of points: local minimum points and local maximum points. Yes. So what is the meaning of a local maximum? Can you give me an idea? So for example, here, this point that you see on top is a local maximum point of this function f of x. Why we call it a local maximum? Because the height of this point is greater than the height of the points in the vicinity. Yes? So isn't that clear? Yes, if I go a little bit to the left, the value of the function decreases. Even if I go a little bit to the right, the value of the function again increases. So the value of the function exactly at this point is higher, if the value of the function is greater than the value of the function in the vicinity of that point. Okay, so but you might have this situation. So yes, you might have this situation as well. Yes, so this is also a local extreme point. That is also a local extreme point, even though this point is higher than this point. Okay, so there are two notions. One notion is an absolute maximum, absolute minimum. We will talk about that later. But today we want to just about talking about local maximum points and something like this here, local minimum points. So when I say that a point is locally maximum, it doesn't mean that it is greater than every other values. It means that if you look around that point is higher. Yes. And when you say that something is a point is a local minimum, it means that when you look locally around that point, that is lower. Is that clear? That's a difference between an absolute maximum and minimum with this. And when I say extreme point, it means either maximum or minimum, because most of the arguments are valid both for maximum and for minimum. Instead of saying, okay, oh, maximum and minimum all the time, I say extreme points. Yes. And then I told you that in this lesson and in high school lesson, actually, you are only dealing with functions which are very well behaved, polite functions. Yes, well behaved in mathematics means they are continuous and differentiable. Okay, continuous, it means that I can draw the graph of the function with one pen stroke. And then differentiable means that I have a function without any sharp points. Okay, so and the sharp point is something like this. For example, this can be considered a sharp point. Here, the problem is that, of course, the function is still continuous. I was able to draw it with one pen stroke, but the function is not differentiable here. You can also understand it a little bit. The reason that this function is not differentiable here, because can I draw a tangent line to the graph at that point? It doesn't make sense, yes? So you might say that, okay, all of them are tangent lines. Yes, this is a tangent line. I don't know, this is a tangent line. But you can feel that these are not tangent lines, yes? They are not touching the graph. But you can have half tangent lines, yes? For example, you can say that, okay, I don't have any tangent line, but this line is tangent to this part, and then this line is tangent to this part. And the slopes immediately before and immediately after are different. So these kind of points, the function is not differentiable here. If this point is a point A here, if I ask you what is f prime of A, it is good to know that you should understand that the answer to this question is that f prime of A doesn't exist. Okay, the function is not differentiable at that point. So for some reason, these are excluded from high school studies. So these are not very difficult ones, but you need to understand a little bit more about the differentiability of functions. So this is why they have excluded this. But might be I can give you this in the exam and I ask you find the local maximum points. Is this a local maximum, by the way? Yes? Do you think that this point is a local maximum? If this is the, because by the way, everything that we are discussing and making it hard, it would be easy even for primary school student to catch. Yes, if I give the graph of the function and I say that, okay, which is the highest point, everybody knows about. Okay, so the reason that we are dealing a lot of time to understand these things, because the problem is that we don't have the graph. We are doing all these things to be able to draw a good graph. Okay, but if the graph is clear for answering these questions are very simple. Do you think that this is a local maximum point or not? Come on. Yes, it is. Yes, because this point, the height of this point is higher than the point in the vicinity. Okay, do you agree with that? Okay, so this is also a local maximum point, but there is a big difference between this local maximum point and these local maximum points that in your book you want to study. What is the main difference? I just mentioned it, yes?
They are differentiable.
Differentiable, and the derivative is 0. Yes, here I have a horizontal tangent line, I have a horizontal tangent line, and I have a horizontal. They are differentiable, and the derivative is equal to 0. But here the derivative does not exist at all. But still, it's a local maximum. So you will not be able to detect in your lesson analytically, not graphically. In the exam, I can give you the graph, and I can ask you locate all the maximum points. Okay, so then this is a maximum point. Looking by the, but analytically, if I give you a function, I will not give you functions that whose graph are of this type. Yes, these are beyond the scope of this lesson. Okay, I can play around a little bit with this concept. Let us see how do you understand that. This might be a little bit tricky. What do you think about this point? So let us do some game. Yes. Yeah, here, this is why this graph that I am drawing is not continuous. And then I put this point on top of this. Okay? And then I ask you, for example, this is the graph of a function, y equals to f of x. And then this point is a. Now I am asking you, if I ask you what is the coordinate of this point, the coordinate of this point you don't need to be worried about the coordinates. Okay, now I'm asking you, is this point a local maximum or a local minimum or neither of them?
Neither. This is not in the graph.
No, it is in the graph. The graph, so the graph is not continuous. This is why. So when I draw something, this point is filled. If it was not here, you are right. That was not part of the graph because it has been excluded. But when I put this dot on top of the hollow part, it means that my graph consists of this continuous part and on top of that one single point. So if you ask me, is this graph continuous? I would say no, because the whole graph cannot be drawn but with one pen stroke, yes? I have to lift my pen, put it here, and then again continue. So it's not continuous. Okay, so this is why you will not analytically analyze these problems. But from the picture point of view, I don't know. I was trying to think a little bit about to make something strange a little bit. But do you think this is a local maximum or a local minimum or neither of them? Yes?
You could say it's a local maximum because none of the points next to it are.
Yeah, exactly. So if you stick to the definition, this point, even though seems strange because the function is going down, but this point is a local maximum. Why? Because the height of this point is this. What is the height corresponding to this point? The height corresponding to this point is this. The height corresponding to this point is this. So you can immediately see that at this point, the function is jumping up, but at the vicinity of that point, the height of the function is lower. Is that clear? So this is a still, even though it seems to be minimum, but it is a local maximum. Yes, based on the definition. So what do you think about this? For example, a function comes here. So this is why, if we want to talk about continuous functions, there are some different techniques that we need to use. Okay. So for example, what do you think about this function? So what is this one? What do you think about this point? Is this point a local minimum or a maximum? The point corresponding to A, which one, by the way, which point on this graph corresponds to A? This one or that one? This one is the hollow one, so it means it is excluded. So this one is the point on the graph. Yes? So now tell me, do you think that this point which corresponds to A, is that understandable for everyone? Is this graph understandable? I have a graph which is two parts. Yes? One part is coming up to here, one point excluded, and then one part of the same graph starts from here, this point included. So do you think that this point which corresponds to point A, which point corresponds to point A? Of course, the filled one, not the hollow one. Is this a local minimum or a local maximum? It's a local minimum, yes, because it is the height here is smaller than the height from the points on the right, and it is much lower than the points on the left. So that is also a local minimum. Is that understandable? The height of that point is lower than the height of every point in the vicinity. Of course, the height is closer to the height of these on the right, but it is much smaller. No problem. It is still smaller. Yes. And what do you think about this situation? What do you think here? For example, it goes up, and then it's something like this. What do you think here? What this point means? So if this is point A. Is this a local maximum or a local minimum? The point corresponding to A.
Neither.
It's neither. Yeah? Because if you stop here, this is the height of this point. The height of this point is greater than the height of the points on the right. Yes? But it is smaller than the points on the left. Yes? So it is neither a maximum nor a minimum. Okay, so they might be a little bit confusing. You need to be careful, but you don't need to be worried about these situations when we want to work with real functions. By real functions, I mean that their value, they are also real functions. So I need to correct myself. If I give you the formula of a function, none of these situations will happen for those functions at the level of your lesson. You only deal with continuous and differentiable functions. You see that if continuous means one piece. If I give the opportunity to the graph to break down, then the things becomes a little bit hard. Okay, and now let us go back and try to understand how we can find. My goal is to find the local extreme points, local maximum points, local minimum points. Yes. And the terrace points. So let me draw all of them in one diagram. So terrace points are also two types. Both of them are called terrace points. So one terrace point is something like this. Another type of terrace point is something like this. So I think this is not a good graph. This should the tangent should be horizontal. Yes. So let me first draw the tangent line and then draw this graph. So these points that you see are important for us. Let me draw all of them in one picture. So this is a local maximum. This is a local minimum. This is a terrace point. Let me write terrace. Okay, and this is also a terrace. Okay, well, and then you understand. So, by the way, what is the similarity between this point, and that point? What is in common between them? Yes.
All the derivatives are zero.
All the derivatives are zero because all the tangent lines are horizontal. Okay. And then, do you understand that none of the other points on the graph have this property? Is the derivative zero here? No. Is the derivative zero here? No. So the derivative of this function is not zero except this local maximum point, local minimum point, or a terrace point, a terrace. Yes? So it means that if I want to locate them, it is very simple. I need to ask myself where the derivative is equal to zero. Is that clear? When I ask where the derivative is equal to zero and find those points, it means that I have my candidates for these type of points. This is one thing that's very clear. But then I need to be able to classify them. Which one of them? Because the graph is not in front of your eyes. If the graph is there, nothing is being done. Okay, it's easy. You don't have the graph. You have only the formula for the function. You want to find these points. So the first step, which is very intuitively clear from this picture, is to find those points for which the derivative is equal to zero. So what does it mean? It means that you calculate the derivative as you have learned so far, put it equal to zero and solve that equation. You get some bunch of numbers. Okay, but those numbers are candidates for these points. We don't know which one is which. Okay, we want to realize which one is a local maximum, which one is minimum, which one is a terrace point. And that is very clear here. How do you know? Do you remember what I told you in the first motivating lesson? So how should I understand that a point is a local maximum? You just look at the behavior, because this chapter has a lot of instructions in it. And if you don't connect the instructions to the intuitive picture, you will mix them up. They are very, very close. But you don't need to memorize anything. What is the difference between this one and that one? What is the common thing is that the derivative of all of them is equal to 0. But what is the difference between this point? Because by eyes, everyone can see that this is higher than the vicinity points and this is lower. How do you understand this is happening? What is the difference between these graphs? Yes?
In the one to the left,
Yes.
the derivatives have a positive k value before and a negative k value after. And the opposite.
And the opposite for this. So it means that the sign of the derivative is changing. Here, if I ask you what are the derivatives before this point, all the derivatives are positive, yes? Because if you draw these tangent lines, all of these slopes are inclined in this way. All of them are positive. So the derivative on the left-hand side is positive. But all the derivatives after that, you see the tangent lines, all of them are oriented in this way. All of them are negative, yes? So the derivative after that is negative. And then this is the other way around, yes? So if you look at the points before, the situation is different. The function is decreasing. It means that the derivative is less than 0. And here the function is increasing. The derivative is greater than 0. So it means that the derivative changes its sign in passage of this point. From positive to negative, it is maximum. From negative to positive, it's minimum. But here, the derivative doesn't change any signs. The function is decreasing before this point. So it means that the derivative is negative. What is the behavior of the function even after that? It's also decreasing. Yeah? So the derivative is again negative. But here, the derivative before that point is positive because you see the function is going up, it's increasing, and after that, again, the function remains increasing. So that intuitive picture is the content of what is called the first derivative test. That's it. The first derivative test. So now, can you cook up an algorithm? So what should we do if we want to do this? The first step we do, what is this? I give you a function f of x. So let me write this. How to determine local extreme points. Extreme and terrace points. Yes? So this is the answer. So that is called the first derivative test. The reason that this is called, there is another test that we will study later, that is called the second derivative test. So what is the first step? The first step is determine f prime of x. The second step, solve f prime of x equals to 0. Yes? Let x be equal to a be an answer. If I ask you, is it guaranteed that this is a local extreme point? It's not guaranteed because it might be a terrace point. Let be a solution, yes? Then what you need to do, you need to set up a table. This is called set up the sign table. So what is this sign table? The sign table consists of 3 rows. The first row by convention is x. The second row is reserved for the derivative. The third row is reserved for the function. And then you put this value of a here. You know the derivative at this point is equal to 0. And then you calculate f at point A, so it becomes f of a. There are 4 possibilities, yes? There are 4 possibilities. If the derivative before that is positive, let me go yes, positive and then negative, the derivative goes, you need to draw these table completely. So this arrow means the function is going up, this function going down. So this means that this is this point a and f of a is a local minimum. Yes? If this happens that the function is negative before, the derivative is negative before that, and after that it is positive, then the point f of f a and f of a is a local minimum. And if this turns out to be negative, negative, then positive, positive, in both cases, a and f of a is a terrace point. Okay, so what you need to know for the exam is this recipe. But I don't want you to memorize that. You need to visualize this picture in your head, and then immediately you see this content. Okay, so if you want, this is an algorithm to determine local extreme and terrace points. Let me emphasize, this is always for your lesson, for continuous and differentiable functions. So this is, I wrote it in red. This is always the case. If I forget to emphasize that, this is implicitly should be this should be implicitly understood from the concept.
The first one is a local maximum, right?
Okay, thank you very much. Thank you. Okay. Okay, now let us do some exercises here. So this is the example that I want to talk about. So let me. So example, this example is very important. This is something that you need to know. Determine local extreme points if any of the following graphs of the following functions and classify them. So what does it mean? It means that which one is a local minimum, which one is a local max. Okay, so let us start solving some problems here. So number one, let me start with a very simple one. F of x equals to, for example, x squared plus 4x negative 1. This is something that you immediately understand that this is a parabola and it should have a minimum, yes? Why? Because if you remember Math 2C lesson, because this is positive, this parabola should have a minimum. But forget about those things, let us consider it using this technique. So what I need to do, I need to take the derivative first, which is 2x plus 4. Yeah, please interrupt me if you don't understand something. And then you put that derivative equal to 0, yes? I want you to understand why. Because these points have this thing in common, that all of them have horizontal tangents. So this means that 2x plus 4, I put it equal to 0, and then x becomes what? X becomes negative 2. I put minus 4 there and then divide by 2. So this is one of the points. So it means that I have one candidate. This candidate might be at this stage, might be a local maximum, might be a local minimum, or might be a terrace point. It's not clear yet. So what should I do? I need to set up a table. This is called the sign table. The sign table by convention has 3 rows, x, f prime, and f. Here, I prefer to write minus. This is not in your book, but that is a symbol. It is good to know. This is the infinity symbol. It means that the values of x goes from minus infinity to infinity. That is correct, yes? Because there is no limitation for this function. If I ask you what is the domain of this function, what does it mean? It means what are the numbers that you can put instead of x? You can put every number instead of x. So your choice can be any number from minus infinity to infinity. I would prefer to write them, but in the book they haven't written it down, so it doesn't matter. And then you have this number, you put it somewhere here. You don't need to be very symmetric or very pedantic in drawing this graph. And then what will happen below this for f prime? I myself put f prime equal to 0, and I got this answer. So it is clear that if I put minus 2 in f prime, the answer would be definitely equal to 0. Yes? And then I want to write some number here below that. Okay, I need to go to the function itself. This row is for the function. I go to the function, I put minus 2 in this function, so you can do it in a scratch paper. Minus 2 to the 2 is 4. Minus 2 times 4 is minus 8. And then I have minus 1. So it becomes minus 5. Yes, so this number is minus 5. So this is a little bit tricky. I want you to learn that. So I want to know which side is positive, which side is negative. Okay, I want to determine the sign of the derivative. So the idea, I will talk about the idea, but I will tell you why this works. Okay, I am telling you that if you want to see is it positive or negative, just choose a random number in this area. What do I mean by in this area? It means any number from minus infinity up to minus 2. Just choose a random number. Of course, you can choose minus the square root of 10, for example, but there is no reason for that. So the best choice probably is minus 3 here. Yes? So I will choose minus 3, but be careful. This you don't need to be confused. This is the row for f prime, and this is your f prime. So you can go to scratch paper, choose a random number minus 3, and put it in the derivative, because this is the row of derivative. Sometimes I make mistake myself, I put it here, but be careful. Put minus 3 here, so 2 times minus 3 plus 4. Convince yourself that this is positive or negative. What is that? This is positive, and a positive number is added. What I'm saying is that you can calculate, but that is not necessary. You just need to see if it's positive or negative. Okay? Anyway, let me calculate. 6 plus 4 is just what? No, I made a mistake, yes? This is positive too. Yes? This is negative, so this is negative, sorry. So this means that you can put a negative sign here, but this is a little bit tricky, yes? Because I just checked for one single number, and it turned out to be negative. But I am claiming that, don't worry, everything would be negative. So this is something that I want to talk about later. But just learn the trick. The trick is choose a random number from here. When you are dealing with continuous and differential functions, this will work. So you just pick a random number and calculate your derivative for that random number. If it is positive, that's okay. Everything would be positive. If it is negative, everywhere it would be negative. But it is not clear. I need to discuss about why this is the case. And then do the same thing for this area. So what should I do? I choose a number bigger than minus 2 randomly. So probably the best choice is 0. Yes? So 0, I put it in the derivative. So what is the answer? The answer is 4. 4 is positive, and then you put positive here. Again, I need to make sure why this is correct. I only checked it for one value, but I'm claiming that this will remain the same for all values, okay? So forget about this for the time being. Just learn this trick, and then we'll just talk about that, why this is correct. So here the function is decreasing. Here the function is increasing. So it means that this point is of which type? of this type. It's a local minimum, yes? So this you need to write. So this is the answer that you need to write. The point, when you say point, it is very important to understand. The point -2 and -5 is the only local extreme point, and it is a minimum. Even if you just write it is a minimum, local minimum, that's okay for me. But I just want to emphasize this is the only local extreme point for this function. You can just simply write the point -2 and -5 is a local minimum. Okay, but let me ask you something. If I ask you what is the minimum value, these are the things. If I ask about the point, I need both x coordinate and the y coordinate. That's the meaning of a point, yes? But if I ask you what is the minimum or what is the minimum value? Minimum, or I would say minimum value. What do I mean? I mean the value, which is -5. So this is -5, okay? And when I say, I can say that when it occurs, you say that it occurs when x is equal to -2. When this minimum is achieved, or this occurs, or whatever. So let me just clean it. This minimum is achieved when x is equal to -2. So these are not part of the solution to this problem, but I want you to understand. If I ask you about the point, you have to express both x and y coordinates. If I ask you the minimum value or the minimum, I mean the y value. When I ask you this minimum is achieved where, you should say x equal to -2. So these are three different sentences that you need to use. Is that clear? So this is a prototype example. We want to increase the level of difficulty now a little bit, but this is what you need to do. Okay, but before that, let me talk about this. Why do you think this is the case? If I just choose one random point and determine the sign of the derivative for that random point, then I can make sure that it remains all the way the same. I don't need to check any other points. So there is one answer to this is that if this is going to change in the middle, for example, we checked for one number, it was negative. But assume that it starts changing somewhere we didn't detect. Okay, it turns into positive after a while or some point. Why this cannot happen? Because we know that for some point it was negative, and then if it turns out to be positive at another point, it means that here the function was decreasing, and then here the function is increasing. And because the function is continuous and differentiable, if this is going to happen, it means that this function should be something like that. Okay, and it means that there is another point which the function is horizontal. So it means that you should be able to detect another point at which the derivative is equal to 0. Yes. So this is not happening because you just only got one answer. Because there is only one answer. If this, for example, I checked, it was negative. Let us say that a little bit to the left, it turns out to be positive. Then you can say that, okay, this part function is increasing, that part function is decreasing, if that is going to be the case. And it means that somewhere in between, there is another horizontal tangent. So it means that there should be another number somewhere here for which the derivative is equal to 0, but this cannot happen because I just put the derivative equal to 0, and that is the only answer. This is one way of understanding this, but a better way of understanding is this one. If you have a continuous function, so I assume that I have a continuous function It goes up and down, for example, here. So these are the roots of the function. If this is the function f of x, if I ask you what are the roots, what are the solutions for this, you would say a, b, c, for example, d, assume that it continues in this direction and it continues in this direction. A, B, C, and D are, for example, the roots of this equation. But because this function is continuous, if I have two consecutive roots, the function is always on top of the x-axis, or it is always below the x-axis, because the function is continuous. That's very easy to imagine, yes? If I draw a continuous function any way that you like to do it, if you have two consecutive roots for the function f of x equal to 0, then between these two roots, either the whole function is above or the whole function is below. So what does it mean? It means that if you choose one random point here and calculate, it turns out to be positive, it remains positive everywhere between these two. So it doesn't matter, you check all of them. And if you just choose a random number here, for example, between these two, and it turns out to be negative, it remains negative all the time. And that is the continuity. So if you relax this condition, this is why it becomes a little bit harder. Is that understandable? So here, the derivative is a polynomial. Polynomial functions are always continuous. And I found an answer for that. And when I check something and it turns out to be negative or positive, it will remain negative or positive all the way around because there is no other roots. The only way that the function can change sign is to have a root, yes? If I want to go from a negative value to a positive value continuously, it's inevitable. I have to cut the x-axis somewhere. So if the sign of a function, of a continuous function, is supposed to change, it means that I should have a root somewhere. But there is no root because that was the only root. Is that understandable? You don't need to be worried about that. If you don't care about these things, you can just memorize that. You just pick a random number and check that. If that's negative, it's everywhere negative, and it's positive, it's everywhere positive. Okay. Now let us start solving more interesting problems. Okay. So number 2. So I have just designed some questions, so let me write them here. Let us talk about this function. F of x is equal to x to the 4 minus 8x squared. What is the first step? Let us do it together. The first step is to take the derivative. It is 4x to the 3 minus 16x. Okay, the next step is to put it equal to 0, equate it to 0, and solve the equation. Okay. So how should I solve this equation? So these are not new lessons. If you have difficulty in solving these equations, that's a different problem. So how should I solve this equation? I should factor it out. Yes, it's the third degree equation. What can I factor out? I can factor 4x out. And what is left for me here? It's x squared. And what is left for me here? It's minus 4. I put it equal to 0. And then, according to the zero product rule, either the first one is 0 or the second one is 0. And if this is 0, what does it mean? It means that I have x equal to 0. This is one candidate. I don't know this. Is it a local maximum or a minimum or a terrace point? Here, how many answers I get? I get 2 answers because x squared is equal to 4. So this means that x is equal to plus or minus 2. So now I have 3 candidates. but still I don't know which one are the real local extreme points and which one, if any, of course, is a terrace point. And even if they are local extreme points, I don't know which one is maximum, which one is a maximum, and which one is a minimum. And then you have to draw the sign table. If this is going to be in the exam, these are the different parts you have to do. Okay, so yeah, because the board is small, so let me just do it here. But here, the table is a little bit longer because you have 3 candidates. So again, the first row x, the second row f prime, the third row is f. If you want to, you can write minus infinity up to infinity, yes, because I don't have any limitations for the numbers that I can put. I can choose any number from minus infinity to infinity. And then you need to keep the order. This is very important. Which one is the lowest number, which is one, the smallest one is -2. And the next number is 0 in my list. The next number is 2. Below these things in the second row, this is always 0. Why? Because I myself put the derivative equal to 0, I got these answers. So it is clear that if I put these numbers into the derivative, the answer becomes 0. But these 3 numbers below them, you have to calculate. Using which rule? The rule of the function. So yeah, that is a little bit problematic. You can use, of course, your calculator. You go to scratch word paper. And the good thing is that it doesn't matter if I calculate it for 2. That's also the same for -2 because it is not sensitive to the sign. And for 0 is also super simple. If I put 0, 0, this is also coincidentally 0 here. What about 2? If I put 2 here, it becomes 16 minus 32. Agree? So it's minus 16. And here is also minus 16. Of course, I can also teach you a trick. I don't want to do that because, for example, from here to here, is the function is increasing or decreasing? So the logic is the other way around. So don't use these tricky ways. Yes, the function is increasing. So this is positive. Yes. If it is going to be negative, then it means that the function is decreasing. Okay. So this is working. But yeah. Because in more complicated functions, this can be a little bit tricky. Because you know that, by the way, a local minimum can be higher than a local maximum. Yes. So, for example, if this is a local maximum, then you go here, and then you go here, and you go here. This is a local minimum, but still it is higher than this local maximum. So, but this cannot happen actually here. So, from here to here, what happens? It's decreasing. Yes. You're going down, so definitely this is negative. But the logic is completely the other way around. You need to determine the sign first and then understand which one is which. Okay? So let me not to do that. Okay. So how should I do that? I pick a random number before -2, for example, -3, and put it in the derivative. So what is in the derivative? If I put -3 here, this term becomes positive 48, and this term becomes negative 108. So it is negative. Yes? And then -2 and 0 is -1. If you put -1 here, it's positive 16. It is negative, so it's positive. That was the prediction was correct. And between 0 and 2, I put 1. 4 minus 16. 4 minus 16 is what? -12, so it's negative. And after 2, I put, for example, 3. This becomes positive. So this means that here the function is decreasing, here the function is increasing because I am seeing the signs now. So what is the nature of this? The nature of this is I have -2 and -16 to be a local minimum. And this is also a local minimum, but this is a local maximum. Yes? So I would say that -2 and -16 and 2 and -16 are local minimum points. And the point 0 and 0 is a local maximum. By the way, this is not part of the lesson right now, but you can sketch the graph of the function. Yes? So how can I use this data to sketch the graph of my function? Everything I need is here. Sketching, by the way, I don't want to have a precise graph. This is not part of the solution to this problem. The problem ends here, the solution. But here, how should I do that? These are points that they are very important for me. So -2 and -16. For example, assume that here is -2 and -16 is somewhere here, for example. So this is a point -2 and -6. What is the behavior of the graph of the function there? It is of a minimum type. Yes? So it means that around this point, the behavior is something like this. I don't know exactly. Might be it is very sharp, might be it is very flat, or something in between. Okay? But the behavior of the function at the minimum is something like this. Something like this is around that point. The graph of the function there is something similar to that. For 0, 0 is a maximum point. So it means that 0, 0 is here, of course. So around this point, the function looks like this. Yes? And then I have another point, 2 and -16. 2 and -16 is 2 here is again, and -16 again below there. It's also a local maximum, so it's something like this. And then I told you, if you look at this function, it's a polynomial function, it's continuous. So continuous function goes very smoothly. So what happens? You have a rough idea of the graph of the function. So the function, before this -2, the function, when you are at -infinity, so it means that when you are very, very left, the function goes down and down and down until it reaches to this point. So I don't know, it starts from here, and goes down, and then up to here, then it goes up, and then it goes down, and then it goes up, something like this. Something like this. I'm not saying that this is 100% correct, but this captures the most important essence of the graph of the function. So this is a way that we do it. So, but this is, I think, I don't know how this is in your lesson or not, but I think that is something not very hard to understand. I think sketching of the graph is also one part of this chapter. I forgot, is it math 4 or math 3? But anyway, this is a very good way to draw the graph of the function. Okay, so let me change the function now. Give you another example. Hopefully this example let me see. Let me give you this example. F of x equals to 2x to the 3 minus x to the 4. Let us solve this example. Okay, I want to know the situation of this graph. So what I do, I take the derivative again. So it becomes 6x squared minus 4x to the 3. Okay, I would prefer to stop here because that is a good example. I want to finalize the problem yourself. It's not hard at all. But let me wait for you a little bit to finalize this. I mean, put it equal to 0 and try to find the roots, set up the table, and realize which points are local maximum and which points are local minimum. And if you are more interested, I don't know, the book doesn't talk about exponential functions at all, but I actually made some examples. These are possible at the level of your lesson. If you are interested, we will also solve these too. I don't know, these examples haven't mentioned in the book, even though you know everything, to be able to solve them. I think it's also good exercise. Try to sketch the graph of the functions, even though that is not part of this lesson here. Okay, did you finish this one? Yes or no? Did you finish the first one or not? Yes? Okay, is there any terrace point for this function? Yes or no? Haven't you finished?
I got one terrace point and also a local max.
Yeah, I think that's correct. So there is a terrace point here, yes? Why is that the case? Because I'm supposed to put this equal to 0. And then what happens is that I have 6x squared minus 4x cubed equal to 0. Then I factor a 2x squared out. Then what happens here? This becomes 3, and then minus 2x. Am I right? Yeah, this number is a little bad number, yes, I do. Anyway, so I have done everything correct here, yes. And then this means that either x is equal to 0 or x is equal to 3/2. Do you agree? These are the candidates. I hope that you don't have difficulty to understanding this. Yes, either this one is 0 or that one is 0. This one is 0 gives you x equal to 0. This one equal to 0. 2x is equal to 3. I divide by 2. This is my candidate. And then I need to set up my table. So here I have x, I have f prime, I have f. There is no limitation in my function, so if you want to, you can put these signs here, minus infinity, infinity, and the smaller number is this one, the bigger number is that one. And of course, this is 0, 0. And then for this one, I put 0 in my function. This I get 0. Then I put 3/2 in my function. I need to do it in a scratch paper. So 3/2 to power 3 minus 3/2 to power 4, yes? So this becomes 27. 2 to the power of 3, well, that one is gone, so it is 4. Yes? And here it's minus 81, 16. So then if I calculate this by the common denominator 16, it becomes 108 minus 81. So that is 27/16. Yes? So the answer is 27/16. Agree? Did I do it correct? Okay. Now you go here. Let us, of course, it is clear. What would be the function from here to here? Can you tell me without knowing about the sign, the trick? This is 0, and then you see that the function has increased. Yes, so we know that the function is increasing here. But so of course, this you can use the trick here. But for this one, you need to have a good understanding of limits of functions in infinity. So this is why I'm saying not to do that, because you don't know what's happening here. So if I put plus infinity, what do you think will happen for this? These are some extra information that I'm giving to you. Don't worry about this. What happens if I put very, very big number? Do you think it would be a very big number or a very small number? Yes?
Very small number.
Very small number. Why? Because this is power 3. This is power 4. Power 4 is more stronger. So if you put a very, very big number, finally this will dominate, even though the coefficient here is 2 times larger, but 2 is not that important when it comes to exponents. So this means that when I put this positive infinity, this becomes negative infinity. And when I go from here to negative infinity, definitely I am decreasing. But don't do these tricks because these are not in the book. So let us just do what is inside the book. I need to choose a random number before 0. The best choice is -1. I put -1 here. This becomes positive 6, positive 4, so it becomes positive. Between 0 and 3/2, the best choice is 1. I put 1 here, 6 minus 4. Again positive. And the prediction was also correct. Do you remember? And then from 3/2 to the other to infinity, I think the best choice is 2. Yes? If I put 2 here, it becomes 16 minus 16. No, sorry. This is my mistake again. I put it in the function. I have to put it in the derivative. So I put 2 here. This is 24. And this is how much? 32. It's negative. So then this is positive, but it remains positive in passing through this point. So this is not a real local extreme point. It's a fake one, yes? And this goes down. This point is a terrace point. Of which type? Positive, positive. So the terrace point is something like this for this point. Yes? But this is a local maximum as you predicted, yes? So let me write 0, 0. You need to write this as the answer. 0, 0 is the terrace point. And then the point 3 over 2, 27 over 16, which is a bad number actually, is a local maximum, yes? So this you have to write at the end. Because if you just leave it to me, that's not enough. You have to write this down, okay? 0, 0 is the terrace point, and this point is the maximum. Let us do some sketch for this graph, okay? Let us see what will happen. But these numbers are very bad. Computer is better, of course. But we can actually understand what's going on, yes? So here, 2 points are important for me. 0 and 0, which is a terrace point of this type. So what I know that around this point, the graph should be something like this. Around that point, yes? But what is the point 3 over 2? It's 3 over 2, I don't know, it's 1.5, but this is a little bit smaller than 2, okay? So you don't need to be worried about the details. So this is 3 over 2, and assume that this is somewhere, somewhere here. 3 over 2, somewhere 16, 27 over 16, yes? And then you have this point. And that point is a local maximum. So around this point, this should be like this. Okay, then it becomes clear. If you want to do it smoothly, how should I do that? Yes? Okay, for example, do you think, can you just sketch the graph? You see from here to here is very clear. They should be connected, okay? And then what is happening after 3 over 2? After 3 over 2, the function continues going down because it remains decreasing. So there is no coming back again. So this function will go, of course, if you do it with computer, you find the exact value here, but we don't care about these things right now, okay? So it will go down forever. But what is happening here? Before 0, the function is coming up until it reaches to this point. So this is clear that this will also go forever. Okay, so this type of incline was very important. If you just draw it like a parabola, this is not acceptable. But this is how much we want to, we don't need to do it very precisely. But that is a very nice way of graphing things. You see that, yes? I was able to draw the graph of a little bit complicated function as well without using GeoGebra at all. Okay, so that is actually, now you understand, this is a powerful tool if you want to sketch the graph of the function. And it is always very good if you do it with GeoGebra to see the exact graph and compare how much you have done it correctly. Okay, so let me solve one of them for you. I don't know, none of them is in the book, but you can solve them. I don't know why they haven't given. The examples in the book are always polynomials, okay? But as far as the functions are continuous and differentiable, you know how to do them. And the exponential functions, remember, polynomial functions are continuous and differentiable everywhere. Another category of important functions are the class of exponential functions. Those are also differentiable and continuous. Let us do one of them, okay? And we don't have that much time, so let us do it together. One of them I will solve. The other one, you can use it as a home exercise. The first one I will solve it for you. Okay, so f of x is equal to e to power 2x plus e to power minus 2x. Okay, now help me. The first step is to differentiate. The differentiation, you need to know another rule, the rule of exponential functions, which you already know. The derivative of this function is 2e to power 2x. The derivative of this function is minus 2e to power minus 2x. Everyone agrees? This is the derivative. What I need to do, I need to put the derivative equal to 0. Might be this is the reason that they don't ask you to do this, because solving exponential functions might be a little bit hard. But this is not of hard types. So can you tell me how should I solve that? 2e to power 2x minus 2e to power minus 2x is equal to 0. Can you tell me how should I solve this equation? I want to find x. Any ideas? At least what is the first step? Yes?
I would move it to the right.
Yeah, that's why I will do the same. So 2e to power 2x, and then what is the next step? Do you
Divide by
think?
2.
Divide by 2. At least do these things, okay? Then get stuck. Okay. Now, can you tell me how should I do this? How should I solve these equations? It's not hard at all. What is the meaning of e to power negative 2x?
1 divided by e.
What? So why don't you do that? So let us do this. So most of mathematics is coming very natural. I don't know why do you hesitate to write. So what happens is that e to power 2x is equal to 1 over e to power 2x. And then probably you remember this famous sentence of me that I hate fractions. So what I do, I multiply by this to get rid of this fraction. I multiply everything by e to power 2x. What is left on the right-hand side is 1. But can you tell me what can I write instead of this? It's a better.
E to power 4x.
E to power 4x. E to power 4x is equal to 1.
4x equals to ln of 1, and then you divide by 4.
ln of 1 is a famous number. ln of 1 is
0.
0. So this means that 4x...
So x equals to 0.
Exactly. 4x is equal to ln of 1. ln of 1 is 0, so this means that x is equal to 0. Yes? And it was also clear from the beginning, it was not clear that this is the only answer. Because if I put x equal to 0, e to power 0 is 1, e to power 0 is 1, 2 minus 2 is 0. But it was necessary to solve it, because 0 was one answer that we were able to guess, but there is no guarantee that this is the only answer. But by this solution, we understand that no, there is no other solutions. X equal to 0 is the only answer. Okay? And then we draw the table. So x, f prime, f, minus infinity to infinity, and then I have only one candidate point. Here, the function becomes 0. Sorry, the derivative becomes 0. And what would be the value of the function? E to power 0 plus e to power 0, which is 2. So this is 2. Yes? And now choose a random number before 0. Don't forget about your derivative. This is your derivative. Now tell me, what would be the answer? Choose a random number. For example, minus 1. A good choice for random number before 0 is minus 1. If I put minus 1 here, first of all, you have calculator. Assume that you don't have any calculator. You don't want to find the exact value. You want to see if it is positive or negative. That's it. So assume that I put minus 1 here. This becomes 2 e to power minus 2. Then this becomes minus 2 e to power positive 2. You don't need to calculate. Is it positive or negative?
Negative.
Negative. Why? Because e to power minus 2 is 1 divided e to power 2. So definitely it is this number is smaller than that number, yes? So this is negative, and that is enough for me. So this is negative. And now choose a random number after 0. The best choice is 1. Put 1 here. So it becomes e to power 2. This is also very simple now. So which one is that now? It's clear this one is bigger, so it becomes positive, yes? So that's positive. So this means that the function goes down here, goes up. So what is this type of point? It's a minimum point, yes? So this function has a minimum. So 0 and 2 is a local minimum. So you see, it is not hard. I don't know why they haven't written in the book. So exponential functions, of course, the only tricky part is that you cannot solve the equation, because exponential functions can be very hard to solve. Sometimes we cannot solve them, okay? But this one you can also practice. Let us sketch the graph of this function. It's a very boring function, yes? It's, let us see, how should I draw this? What is the only important point for this graph? You don't need to be worried except this point 0 and 2. So 0 and 2 is somewhere here. Here, the function looks like this. And what happens? After that, the situation is clear. It goes up and up. So it goes up and up. And before that, the function is going down until it reaches to this point. So it's something like this. But it is not a parabola. If you draw the graph of this with GeoGebra, it looks like a parabola. It is not. Okay, so parabola has a definite meaning. Not everything similar to the parabola is indeed a parabola. It's like that. If I give you an ellipse, which is very, very... so the ellipse is this. So this is the major axis. This is the minor axis. You immediately see that this is an ellipse. But if the major axis is very close to the minor axis, you cannot differentiate it with a circle with your eyes. Okay, that's the same story. If the parabola has a precise definition how a parabola is, but this is not necessarily a parabola. Okay, and this is something that you will later learn. This is called cosine hyperbolic function. So that's a cosine hyperbolic function, of course, multiplied by 2. Okay, any questions? Yeah, I just want, this lesson is not finished. There are some nice examples in the book. I want to discuss about them later. One exercise is very good, so you can check it yourself. I'm just emphasizing. They give you the graph of a function, and they say that this is the derivative of the function, not the function itself. Please try to find, I will write it on a school soft. Go and solve this problem. This is a very nice problem. I saw it in the Oregon. They give you the graph of the derivative of the function, and they ask you about some information about the function itself. Okay? Which is not easy to do. You cannot say that by looking at the graph of the function, I can guess what is the function itself. No, there is no guessing. Okay? But you need to understand how should you extract the information from the graph of the derivative to say something about the graph of the function. Okay? This you can find it in there. I will write it on a school soft. I will talk about this thing later, and then I will give you another type of examples. Then this lesson will be finished. Okay? So I will write on a school soft which page to read. Any questions? Okay, thank you. So thank you here as well.
Ja kommer inte. Jag kommer vara